So how are things going? Like related to this class, how are things going? Homework? The homework for 1-4? The limit stuff where you had to calculate by hand, all that stuff? That was all right? I had like, I think close to 100 views of my homework video. I was pretty happy about that. That's pretty good.
I think I made it a couple times.
You had like 80 of those? All right, so that's encouraging. That means I'm going to keep doing them.
It really helps me out as far as
Okay.
if you like get stuck at a certain place and you're like, you just do this, you're like, oh, why didn't I think of that?
Yeah. So there are a lot of things in this class that you will have to see me do once or twice before you start to understand, well, that's what I need to do when I see it, right? Like, it's kind of picking up the tricks of the trade. And that, yeah, sure.
It was breaking apart this x cubed plus 8 thing. I know you did it in the video.
X cubed plus what?
8.
8?
Like you did like this, I don't know.
Yeah. X cubed plus 8.
Oh yeah, that's the.
I used the sum of cubes formula, which is on your formula sheet. That's on your formula sheet. So I'm using this. And then there's a difference of cubes formula also. The only thing that changes in the difference of cubes is if this is a minus, then this is a minus, and that's a plus. And everything else is the same.
Yeah, but like, how do you take out x2 out of x cubed plus 8? Like, that's what I was confused about.
How do you take x what?
X plus 2 out of x cubed plus 8. That's what I was confused about.
I still don't get. How do you factor it out?
Yeah. Like,
Well,
that was just a comparison.
okay, I think what you're asking is, okay, if I actually do this, what is this? 2x plus 4, right? That's what it turned out to be. And I think what you're asking me is like, how can you see that that comes out of that? I don't know. There's really no way to show you that it comes out other than to do this. If you take, if you divide this side by x plus 2, and you divide this side by x plus 2, this goes away, right? Over here you do long division. And what I mean by that, or synthetic, depending on how comfortable you are with your division. If you rewrite this like this, remember that? And do your long division, you're going to get a remainder of 0. And that means the answer up here is this. And that's confirmation. But you can't just look at this and be like, oh yeah, x plus 2 factors out. That's why it's a formula, because we need to remember that it does factor. Does that kind of answer the question?
Is that bad if you looked at it and you were like, oh yeah, that does?
If you looked at what?
Is it bad that I looked at that and I just recognized it and I just...
No, you want to recognize that as a sum of cubes formula. You want to recognize it that way.
Like,
yeah.
Because you were like, you can't do that. I was like, how do you do that?
Wait, you can't do what?
Well, I thought you were like, you can't.
No. I think what you're asking is kind of like if you have, and tell me if I'm wrong, if you have like x squared minus 4x and you're asked to factor, it's obvious that you can pull x out. Like that's a clear thing to see. But if you have x cubed plus y cubed, it's not obvious that you can just pull x plus y out. And that's actually what happens. We're factoring x plus y out. But it's not visual. Yeah. Okay, good. Do you understand?
Yeah.
Yeah. All right. All right, so we ended class last time, and I think I stopped at a problem we were all kind of freaked out on, right? Is that correct?
Which one?
It was a trig one. Did I end class with the trig one? Or no, I didn't do? Who has it? Let me see. Sine. Yeah, and did y'all do okay with that?
Well, we had more of them on the homework.
Okay, so do you have any questions on those? I'm just wondering, do I go to 1.5 now, or do we have any open questions on 1.4?
You go over that absolute value one?
Yes, were you the one who sent me that? Okay, I wasn't, yeah, that was a great question. It was 43. Yeah, that's a good question. So we have a function g of x is defined to be x squared plus x minus 6 over x minus 2 in absolute value. And we're asked to find two limits. The first one is the limit as x approaches 2 from the right of g of x. Right? That's what we're asked to do. So let's first just rewrite this. Let's plug that function in there. X squared plus x minus 6 over the absolute value of x minus 2. And just do kind of a direct replacement of the 2, and you should get 0 over 0. So you know that there's some sort of issue, so you have to go address that, right? And the numerator is a trinomial, so factoring seems reasonable, right? Limit x approaches 2 from the right. This factors up here to be x plus 3 times x minus 2 over absolute value of x minus 2, like that. Do y'all want to turn the tables, or you can go on the other side if you want? Yes? Now, most students will make this mistake and they will cancel these two factors right now. But the problem is these two are not the same. All right? These are not the same. I mean, I know they look exactly the same, but they're not. And so let's just analyze over here what makes this different than this. So I'm going to put this x minus 2. I'm just going to look at this piece right here. If I am approaching 2 from the right, then I am going to be on a number line. Here's 2. From the right means I'm coming in from this direction, right? So let's just take a sample number to get an idea of what's happening here. 2.0, no, other side. Yeah, that's right. How many zeros do you want? Do you want a lot? 2.01, is everyone happy with that? Okay. Let's see what happens if I plug that in. What's 2.01 minus 2? 0.01 over, okay, 2.01 minus 2. 0.01, but it's an absolute value. Now that's not going to matter because this answer is positive anyway, right? So you take a positive number divided by a positive number, right? This is going to be the same number, right? Same number. So this is going to be a 1. So do you all understand that when we're coming in from the right, these two are exactly the same. The top turns out to be exactly the same as the bottom. Only if I'm coming in from the right. Let me show you what happens if you come in from the left. So I want to change this problem to limit x approaches 2 from the left of x plus 3 times x minus 2 over the absolute value of x minus 2. Approach 2, this time from this way. So I'm going to use something like 1.99. Okay. I'm going to go back over here and plug in 1.99 into this, and let's see what happens. I'll do it up here. I get, what's 1.99 minus 2? Negative 0.01 over, same thing, right? But in absolute value. Right? So what happens there? It's negative, right? Because your numerator is negative, but your denominator, because of the absolute value, becomes positive. And so you're going to get, instead of a positive 1, you're going to get a negative 1. And that would have happened for any number I pick to the left of 0. If I do 1.99999, this top number is going to be negative, and the bottom number doesn't matter. Absolute value is going to be positive. And so the ratio will be negative 1. Are we clear? Sure. Okay, so we cannot cancel these. What we have to do is analyze what's happening from the right and from the left. That's why this was a great question, because I didn't cover anything really like this, so it should have caused some issues. So how am I going to answer this? This one right here, from the right. I know that I can cancel these if I'm coming in from the right, and I will replace that with 1, right? So this problem here becomes limit x approaches 2 from the right of x plus 3, and this is just 5. Direct replacement. However, if I'm coming in from the left, I'm not going to replace this with 1, I'm going to replace it with negative 1. So it becomes the limit as x approaches 2 from the left of x plus 3 times negative 1, which is going to be negative 5. Does that more? Clear now? Yes? All right.
And then that's not it doesn't have a limit because it's got the jump continuity, right?
Yes, does it ask that?
Oh, yeah. Well, it's got like a...
Oh, okay, so it asks in part B, does the limit as x approaches 2 exist? No, because the limit from the left and the right are two different values, positive and negative 5. All right? Questions? Yes?
It's easy for me to think about it, like in front of the absolute value, if I just put like plus, positive, negative, you know, and that way I know that like if I divide by the positive, you know what I mean?
It's like you're going to get both cases?
Yeah.
That's okay as long as you are clear with which case goes with which. Because the fact that we're coming in from the right here, that little plus is not what's telling you this side would be plus. That's not what it is. It is for this particular problem, but if I switch things around just right, okay.
But I mean like how, you know, every time you have an absolute value, like
Mhm.
it's understood that you have like the positive and the negative, you know what I mean?
I'm not sure.
Alright.
Yeah, I'm not sure. Because when you have an absolute value, oh, maybe you're thinking like when you convert an absolute value into like inequality into an equation, there's like the plus. Okay, yeah, I don't want to try and, yeah. Okay, this good? All right, how about the trig stuff at the end? I'm afraid to just move on. I'm really afraid that that's going to come back to haunt you on the test because I guarantee ask questions on the trig stuff on the test. So, number 50? 50? Okay, yes, good. I was hoping I would have a question on something like that. Limit x approaches 0. Sine of 4x over sine of 6x. On your exam, when you have a problem like this, I do want to see the work. If you do enough of these, you start to think that you see a pattern, and you think that you can just put the answer down without doing the work. Danger, all right? Danger right there. So you need to show me all the process. So first, let's let x go to 0. Of course, 4 times 0 is 0, and sine of 0 is 0, so we get 0 on top. Same with the bottom, so we get 0 over 0. So we have to do something. And the only thing we can do at this point is to use that whole sine junk thing, remember? Sine junk over junk. As long as the junk was equal, as long as they both went to 0, this was equal to 1. Even if we flipped it over and put the junk on top and sine junk on the bottom. So what I told you to do last class is, when you see this, is to peel it apart first. Just strip this thing down into its individual fractions so that you can easily recognize where you're getting the division by 0. That's where the problem is happening. So do we all see where the division by 0 occurs? Sine of 6x right there, right? So what I'd like to do is use this thing, or maybe the other way. Right, it works both ways. If I could maybe get this to happen here, then that division by 0 will become a 1 and life will be good, right? So I have to introduce something myself. What am I going to introduce? A 6x on the top, but whatever I do on the top, I have to do on the bottom. So I'm going to multiply the top and the bottom. Pardon? Do 3x? What? I'm going to do 6x and 6x like this, right? And then, because these are all multiplied, right, straight across the top, multiplication is commutative, which means you can switch the order of multiplication. I can simply switch the place of the 1 here and the 6 and just like slide the 6 on top. Can I do that? Yeah. Okay, I'm going to save myself having to write this over and over, so that's the same expression. And I've fixed the problem, right? This is now, when I take the limit as x goes to 0, I get 0 here, sine of 0 is 0. 0 over 1 is okay. It's just 0. That's okay, right? No division by 0 there? So that's not a problem anymore. This, because the junk matches the junk, and as x goes to 0, that goes to 0, and that goes to 0, that limit should go to 1, right? This goes to 1?
So now you have another 0 there.
but I've got this, right?
The x over, and then take another 1, so 4 over 4, and then 4 over.
That's right. So we have to now address this new problem we created. We fixed one problem, we created a new one. But we're going to use this sine of 4x, which didn't even have a problem, right? This wasn't even an issue. We're going to use the fact that if we had 4x down here, this would go to 1. And where's that x going to come from? This x that's causing the problem. So I'm trying to get rid of that x because it's trouble. But if I slide it under here and throw a 4 down there, that's not going to be a problem anymore. So on the next step, what I'll do is I'll slide this under here, and I'll write it again. Limit x goes to 0, sine 4x over x times 6x over sine 6x times, I still have 1/6 out here, right? Because that x just went down. That's a terrible arrow. And I just need a 4. But I can't just do 4. I have to do the same on top and bottom. So I'll put those out here also. 4 here, 4 here, and then I'm going to take the one on the bottom and I'm going to slide that one right there.
Wouldn't it be a 4x?
No, because I didn't introduce an x. I actually used this x, right, that was already there. I just moved it down here so that, see, I'm not going to have division by 0 anymore. That's what I want.
Okay.
But this x underneath here is not going to be a problem as long as I can get a 4 here, right?
But
Which-
if you didn't move the 4, if you didn't move the x from the 6x,
Mhm.
left it as 1 over 6x, you would do times 4x over
You could do 4x, and I've seen other instructors do it that way also, where they just introduce 4x over 4x. They slide the 4x over, and then the x down here and the x up here cancel.
Okay, that's okay.
Yep, that's fine. All right, so
Okay, so it's 1/6 then?
it's going to be 2/3. Yes, because, well, let's see what happens. I have limit x goes to 0. I have sine of 4x over 4x. And then 6x over sine 6x. And then I still had 1/6 here. I moved that 4 over, so I have a 4 on top and a 1 on the bottom. And when I take the limit now, right, this is where I apply the limit. This is where I can use the junk thing. This will go to 1. This will go to 1. And this is multiplication. And then those two fractions are still there. 1/6 times 4 is 4/6, which is 2/3. So what I was saying, people won't show any of this work and they'll just put 2/3. And that's because if you have a sign of something like that over like that, it just becomes these two numbers divided. That's what it is. But it won't always be that. I can make it where it won't happen that way. So show the work. All right? Yes? 27? Uh-huh. Did I do that one in my video, though? I did not? Oh, I did 28.
You said that we were going to do this by ourselves. But you said that that was the same one as 18.
Yeah, except that you have to, well, yeah, it's similar. Okay, so that one threw you off. Let me look at it. We have, today is one of those days where we have some time to cover problems. We won't have many days like this. But today's material over continuity is relatively short. So I don't mind spending a good 20, 30 minutes on this. All right, first thing, if you take the limit, this is number 27. If you take the limit as h goes to 0 here, you'll be left with, if that's a 0, this is just x cubed. And x cubed minus x cubed is 0. So you get 0 on top, and then of course if that goes to 0, then you have 0 over 0. So it's bad, right? Then you have to multiply this out. That would be, since you can't factor, well, I don't know, what did you do? I should ask you what you did. So you multiplied this out, like x plus h times x plus h times, okay. So that x plus h cubed turns out, now should I show this? Should I show this or just write it out? What do y'all want?
I had a question. I factored it all out, but I had a question about, can you use the difference of cubes on this one?
You could. That's why I asked you what you did. You could.
Okay, yeah, I factored it all out.
Yeah. Okay. So you said factored it out. You said factored it out. Just so that since we're in Cal 1, when you do this and you multiply it out, it's called expanding. Factoring is undoing that. So when you say that, you say, I expanded this. All right? So I expanded this expression.
I expanded it using Pascal's law.
You did Pascal. Good. Who showed you that? Oh, okay.
You're wondering, some algebra.
Yeah. There was a reason why. Okay.
Very useful.
Today, yeah, and I'll show it to you. I'll show the whole class later, just so everyone's seen it. That's what that would be if you multiplied it all out, which I'm just going to trust you can do. If you can't, then this is where you make a little asterisk and you come talk to me or you go to a tutor and you just make sure you can do that. All right? Now, that's what the top left of this limit's going to be replaced with. And do not forget, after you've done all that, that you still have minus x cubed. And that's all divided by h. And like all of these limits, what we wanted to do was make sure that the division by 0, right, the division part, that it goes away. So I really would hope that the h would go away, which it does. Because when you do this part, everything that's left has at least one h in it. And that's going to be kind of the theme with these problems. If you ever see an h on the bottom and that's going to 0, you're going to want at some point the h to go away. So that means everything on top is going to have an h in it.
We did this in algebra, didn't we?
I hope so. Yeah. In college algebra, we did these problems. They were called the difference quotient. And we taught you the algebra of the difference quotient. We did everything, like that part of it we did in college algebra. And then all we are doing here is adding this part to it. Yeah. So I'm going to factor an h out of the numerator. 3x squared plus 3xh plus h squared. And then I have the h down here, and that's what allows me to cancel it. And now at this point, I can just replace all the h's with zeros, and I'm not going to have division by 0 anymore. And when I do that, I get 3x squared. And that's the answer. Is that clear? Okay. All right, that's about 25 minutes. I think that's about tops. I think we need the rest of the time for today's stuff. What is today about? Continuity. 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 And I'm going to start today's class by just writing down the definition of a function being continuous at a point, even though it's in the notes, just so that we have it up here on the board. Okay, f is said to be continuous at x equals a if the limit as x approaches a of the function equals f of a. That's the definition of continuity. Geometrically, all this means is that if I go to draw a function, that when I get to a point A, the limit exists, right? This limit exists, which means what? The fact that, forget this side, this limit being equal to something means that, what? What's that? Yes, I'm looking for something a little more detailed. Coming in from the left and the right, it's going to the same place, right? That's what it means for this left side to exist, right? That means that as I come here and I draw this, I don't know where it is, that the limit from the left and the limit from the right are both going to the same place. But that right there by itself is not what it means to be continuous.
No, it has to.
It has to equal, right, where I'm headed has to equal the value of the function at A. So when you go and look at the right side of this equation as being college algebra, the left side of this equation as being calculus. This says, look, I have to head somewhere from both sides, right? But it has to be equal to where college algebra told me the value of the function was. So that means when I come in here and I fill in a hole for this graph, it must lie exactly where it was heading. If that's the case, then this function is said to be continuous at that point. Right? That's the idea of continuity. If you take this out and leave it empty, or you put the dot up here, this function fails to be continuous at A, and we actually say that it would be discontinuous, and this type of discontinuity is called a removable discontinuity. There are 3 types, right? That could have been a good quiz. What are the 3 types of discontinuities? I could have asked for that today. I'm not quizzing you today, though. So this is what it means to be continuous. There are 3 types of discontinuities. First one, removable. Doesn't matter what order we do these. And this is an example of a removable discontinuity. The idea behind the word removable is that it would be a very easy fix for me to make this continuous. Yes?
I thought in the video, the first video, you said that was a jump. Did it jump to that point?
No.
No?
Well, I may have said that it's not continuous because I have to stop, pick up my pen, jump up here and do that, but it's not a jump discontinuity. So maybe the wording, I'll go back and look at it, but I'll show you. The jump is where your actual graph is split and you actually physically jump from one level to another. But this is removable because to fix it, all I would have to do is redefine the function at a single point, right? Only at one point I would fix it, right? Just, hey, at A, be there instead of there. And that's an easy fix. It's removable. Got it? The other type is jump, okay? A jump discontinuity. And a jump discontinuity would look like this. You don't have to have anything filled. Nope. Just if your graph jumps, it's over, right? If you have a break like that, it's over. Now, you could fill this in. That wouldn't change the fact that it's still a jump discontinuity. You could have filled this one in instead. That would still be a jump discontinuity. Or you could have left it completely empty, both of them, and that would still be a jump discontinuity. Or you could have defined it to be down here, and that would still be a jump discontinuity. All right? What makes a jump discontinuity is the fact that the limit from the left and the right aren't the same. Right? The limits from each side aren't the same. There's your jump. These you can't fix easily. Right? Like for this one, to fix it, I just redefine that one point and I'm done. To fix this, I would have to redefine the whole function, wouldn't I? I would have to somehow move this entire graph down to get it to match up. And that means changing the function, not just in a single point, but in a bunch of points. And that's not as easy to do. All right, what's the last one? Infinite. And this is anywhere where you have like a vertical asymptote. Anywhere where your function is going to take off to infinity or negative infinity, as soon as you see that, it's over. Okay, continuity fails. So it would be, something like that. Okay, right away I know I'm discontinuous at A. Now, keep in mind, you could have the function defined at A, and you could have a limit coming in. You could. But if on one side, that's all you need, just one side, it goes to infinity, it's over. You do not have continuity. Pardon me?
Wouldn't that also be a jump?
No, because your limit, to be a jump, the limit from the left and the right are going somewhere, but they're not going to the same place. Here, the limit from the left is not going to a particular value. It's going to infinity. So since this is headed up to infinity, that's why we call it an infinite discontinuity. Understand? Any questions? All right, so the layman's term, or the layman's way of explaining what continuity is that you can draw the function without picking up your pencil. That's what would make a function continuous. So in the notes, in the video, I talk about continuity at a single point. I talk about discontinuities, and then I talk about continuity on intervals. So what I'd like to do is draw a picture for you, and I want to talk about where this function is continuous or discontinuous. So take a minute to copy this down. We'll have a blue function today. All right, here we go. I don't want that. We'll call this blue function f. So the first question is, where is this function f discontinuous? Yeah, let me add a little piece to this so that we don't get confused with what's going on over here. Let's just continue that out forever, okay? All right, so where now?
Also, -3, -2, as it approaches 0 from the left and the right, and at 3.
Okay, so you said -3, right?
That's right.
So at -3, we have a discontinuity. I hope it's obvious that if I were drawing this, I have to pick up my pencil to get over that. And that type of discontinuity is a removable. Right, so at -3, I'm going to even tell you what these are, removable. And the next place where we have a problem would be, well, everything is okay here, right? Everything's fine until I get to here. I have to jump up to get to the next piece. So at -2, we have a jump. Where's the next issue? If I try and go towards 0, x is 0, I have to go up to infinity, so that's going to be infinite. And anything else?
3.
At 3, we have a removable. That good? Now, yes, that could be a test question, which I think you would want, right? I mean, that you would want that on a test.
Would you prefer us to like write out the entire word, or like shorten it? Should be like removal will be R, jump will be
Yeah, I'm very lazy when it comes to things like that. Like I like to abbreviate. So if I'm not abbreviating it, that means you should not abbreviate it. Yeah. Because I truly am, like, I will abbreviate everything I possibly can. Yeah. Okay, I asked you where it's discontinuous. I'm going to have a different question now. Where is f continuous? And this ties into the idea of, we know that we can be continuous at a single point, but you can also be continuous on intervals. That means at every point within an interval. So like if I go over here and I pick this point right here, am I continuous at that point? Yeah, because I'm coming in both sides, I'm headed to the value, I'm good. If I pick the point, let's say right there, same thing. In fact, if I pick any point along this little segment of the graph, I'm continuous, right? Until I get to where? -3. And since I have an arrow there, the implication is that that goes out that direction forever, right? So it appears that I would be continuous from -infinity all the way till I get to -3, and then we're going to always put parentheses regardless on these intervals. For continuity, where's the next place I would be good to go as far as continuity? -3 to 2, anywhere in this little segment, I'm good.
Would you be considered good at -2 because of?
Yeah, see, here's the problem. Let me write that down. The next one should be what? -3 to -2. And what was your name? Luis? Okay, so Luis is asking, should we include -2 since we actually are defined there, aren't we? I mean, we are approaching the value. Here's the problem. If I include it, what's your next interval going to be? -2 to 0, right? So one interval will say all the way to 2. The next one would say from 2 to 0, wouldn't it? And if you include -2 and then continue, that would imply that you can just go the whole way, right? Without even needing to break it up. But we have to because we have a discontinuity. So that's why I say whenever we're doing continuity in here, let's just put parentheses on all of them. 2 to 0, -2 to 0, because we have the infinite. So anywhere in here, I'm nice and continuous, forever up. And then once we get on the other side of 0, it's all good until I get to 3, right? So 0 to 3. And then last one, 3 to infinity. And you could put, if you wanted to, you could put instead of commas, unions in between those, if you wanted to talk about where the function was continuous. I'm more likely to ask you where it's discontinuous. Yes?
Would it be a union between -2 and -2?
Yes.
Even though it jumps?
This tells you it jumps because there's parentheses, not brackets. If I put a bracket here, that means include the endpoint, and I don't want that.
So if we were asked to draw something like this, we would know if -2 was.
You wouldn't know. That's right. You wouldn't know. But I'm not going to give you these conditions and ask you to draw. So the reason why we want to do this is because we want to understand continuity at a point versus continuity on an interval. And that ties into one of the notes from the lecture video, or the course video, which said that we know something about continuity in functions that we've studied already. And that is that all the functions we've studied, where are they? I'm too far. Here we go. Where are functions continuous? All polynomial functions are continuous on -infinity to infinity. So when we talk about polynomials in college algebra, straight lines are polynomials. Parabolas are polynomials. Cubic functions are polynomials. And then you go higher degree and they start getting real whatever. They can do all sorts of things, right? Polynomials. All of these functions are continuous everywhere. You agree? You could draw all those without picking up your pencil. Rational functions are also continuous everywhere, except where perhaps they might not be defined. So if I take something like f of x equals 1 over x, that's a rational function. If I draw it, it looks like this. Has an asymptote here at 0. What this is saying is that Wherever it's defined on those intervals, it is continuous. So over here, when I draw this, right, I can draw it without picking up my pencil. Now, I do have to pick up my pencil at 0, but this next segment, this next piece, is also nice, and I can draw it without picking up my pencil. Okay? What about your trig functions? All of those are continuous on their implied domains. So sine, right? Sine, you can draw that without picking up your pencil. Cosine, same thing. How about tangent? Can you draw that without picking up your pencil? Within the implied domain, it's continuous. But tangent, we do have these vertical asymptotes. But as long as you're not on those, then everywhere you are on the function, it's nice and continuous. Same with secant and cosecant and cotangent, all of those. All exponential and logarithmic functions are also continuous on their domains. All right, so that's just a note. We just need to keep that in mind. If we're ever faced with any of those functions, they are continuous. All right. Now there is a weaker condition than continuity at a point. Does anyone remember what the weaker condition is? I mean, to be continuous at a point, you have to come in from the left and from the right, and you have to be headed to that same value. But there's a weaker condition. Left and right continuity. Right? Left and right continuity. So what do we mean by left continuity? Left continuity means that if you take the limit as x approaches a of f of x, that it has to be equal to f of a, but only from the left. That means you don't need the double side to come in to the same place. This is a weaker condition than continuity is. Left continuity is a weaker condition. So a picture of this would be, as I come in from the left, I have to be headed to some place, and the place I need to head to has to be the function's value. It says nothing about what's happening from the right, does it? So I could have this. This would be an example of a function that would be left continuous at this point A. Right? From the left, limit exists, and where I'm headed is filled in. Right continuity is the opposite of this, right? Limit x approaches a from the right of the function equals f of a. So your picture here would be that. That would be right continuous at a. Yep, they're opposites. Yes?
How does it work with it being considered continuity, but at the same time it's considered discontinuous with the jumps?
Okay, so yeah, that's what I'm saying. To be continuous, the original definition of continuity required that when we came in from both sides, we had to be headed to that point, right? That's very strong condition. To be continuous, that's what we mean.
Okay, so
right?
it's discontinuous left to right, but it's continuous from left or from right based on whichever direction it's coming.
No. What I'm saying is if we say something is discontinuous, it's because that thing wasn't happening. But there is a weaker type of condition that we need to say something is right continuous. That means we don't care about what's happening on the left. As long as from the right it's headed to somewhere and that's filled in, and we throw out what's happening on the left, that's not full continuity, it's like partially continuous. We call it right continuity. And if we have this situation, it's not full continuity, but it's kind of a partial continuity, we call it left continuity. If you have them both at the same time, that's true continuity, because it has to work from both sides. Now, the reason why we like to talk about left and right continuity is for things like this. Look at this function right here. F of x equals the square root of x. If we graph this, it looks like that, doesn't it? Square root of function, or square root of x function. So we all agree that it's continuous everywhere here, right? Because we can draw with that. When you get to this point right here, and I ask you, are you continuous here, right? True continuity would mean you have to come in from the left and the right, right? But you can't come in from the left. Because if you start trying to come in from the left, there is no graph, because this is not defined for negative numbers. So you might say, no, it's not continuous at 0, because I don't have the left, right? It's okay. As long as the function is right continuous at its left endpoints, it's okay. Do you all hear what I just said? If you're at the left endpoint of a graph, as long as you are right continuous, you're good. It's still considered to be continuous. So the function is still continuous at 0. Yes? Okay. So the left and right continuity only take care of, it helps us get around like freaking out when we get to the endpoints of functions, to the end of the graph. That we can still have continuity at 0 as long as the right continuity exists. I'll give you another one. F of x equals square root of 1 minus x squared. Right? That's not as commonly known, but the graph of it's kind of cool. So that would look like this. There's the graph of that function. Square root of 1 minus x squared. That's it. So is this continuous between -1 and 1? Is it continuous? Does it look continuous? Okay. How about at -1? Is it continuous? Yes, because you can't come in from the left. There is no graph. That's okay, because it's an endpoint, isn't it, of the graph? All that we need is right continuity for us to be okay with it. So it is right continuous, so we're good. Is it continuous at 1? Yes, because it's the right endpoint, all we need is left continuity at right endpoints. This is in the notes. Somewhere. Oh, there it was. What happened? Did I go too far? I apologize. Shit, I'm lost. I'm lost in here now.
You're in direct substitution.
Yeah.
Yeah, you have to go down.
I don't know what happened there.
1.5 down.
Boy, I jumped really far. All I did was like barely picked up on my mouse. There it is. Okay. A function f, here we go. Function f is said to be continuous on an interval. It's said to be continuous on this interval -1 to 1, okay? -1 to 1. If it's continuous at every point in the interval. At the left endpoint of the function, at the left endpoint, the function only needs to be right continuous. So at the left endpoint, you only need to be right continuous. At the right endpoint, the function only needs to be left continuous. That's why we can say it is continuous on this entire interval. All right? Any questions on the visual characteristics of continuous functions? I'll tell you if I think it's weird. Go ahead.
How can a right endpoint, something that ends on the right side, not even be continuous at all from the left?
Wait, say it again.
If I'm not coming from anywhere from the left, how can I end on the right side?
If I'm not coming from the left,
And then I'm right there. How would that be open? Oh, it would be open. Like, it's because it makes me think that anything that ends here is going to be right continuous.
is it going to be left continuous? Left. Okay, so f of x equals x squared minus 1 over x minus 1. What about, is this continuous on the interval 0, 1? Right, so if we're sitting here, obviously I can't plug 1 in, right? The function's not defined there. So what would happen is you would have a graph, it would look like this, and it would be open here, it would be closed here. This would be, at the left endpoint, it would be right continuous, but at the right endpoint, it would not be left continuous because you can't fill it in. Therefore, you couldn't make this that. You would have to make it this.
The whole segment be discontinuous.
No, no, just that endpoint. It would not be continuous just at the endpoint. It would be continuous everywhere else. Does that address your question? Yeah? Okay.
Well, it's because earlier, like you said, it was like that except curved.
Yeah,
And we said that it was going to be continuous.
yeah. All right. Everything I've talked about with continuity has been picture related, right? I give you a picture, we look at the picture, it's real cute and coming in from this way, this way. What we want to do is kind of like we did with limits when we first started. The limits, we started with visual, right? And then we got into algebraic limits. We kind of want to do the same thing now. We want to take a look at some functions. We want to talk about their continuity without their graphs, right? So we define the function, and then we see if we can discuss continuity. So let me do, I'm in the wrong section, I apologize. Where's that problem I saw? There we go. I might just make this one up, just for fun. Just to see where you all are. I'm going to define a piecewise function, which from college algebra means I'm going to have a function. It's going to be different functions depending on where you are in its domain. So there's one. Let me see. 3. There we go. So this function is going to behave exactly like this function does as long as we are to the left or equal to 1. Between 1 and 3, it's going to behave like this function. And as soon as we get to 3 and on, it's going to behave like that function. So you have to know how to kind of get a feel for what's happening. You could graph this, right? Well, maybe, right? I'm going to try and do this without any graph. So tell me about this right here. What type of function is this? Quadratic, right? Which is a polynomial. It should be continuous everywhere where it's defined, right? Which it is, right? It's polynomial, we're good. There's no problem with continuity with that. There's no problem with continuity here because that's a line. Line's a polynomial. It's continuous. And then this one right here is continuous also. But when I graph these, since they're all different, I'm going to have, I don't want to graph it, all right? I want to avoid graphing it. I just want to kind of give you an idea of what's happening. Here's 1, here's 3. That's where things are interesting, right? At 1, to the left of it, on this parabola opens up or down? Down. So I'm just guessing here. Maybe it looks something like this. And it's not defined at 1, right? Because there's not a, oh wait, it is, sorry. It is defined at 1. There's a solid dot. And it does something like that, right? I'm guessing. And then between 1 and 3 on this, which is a line, this line has a slope of 1 and it's moved up 2. So I don't know, it would be something like this, let's just say. And it's not defined at 1, it's not defined at 3. Agreed? And then this one is a parabola that opens up because this is a 1 and it's moved down 1. So I don't know, it does something. And that would be only over here. And it's defined. So I don't know. Again, I'm guessing, okay? There. There it is. That's very, very loose graph of what's happening. I actually don't know exactly if these meet up or not. See, by itself, it's continuous. By itself, that's continuous. By itself, it's continuous. The question is what's happening at 1 and 3, where they meet up. Do we maintain the continuity or not? Right? That's the question. Do you understand the question? So here's the function. I want you to tell me where is f discontinuous? It's all right.
Wouldn't you just plug in numbers? Like, you can plug in 4 minus x squared or 1 into the x.
Oh yeah, you could, right? You could just plug in, you could see. But from where we're about to go after this problem, I want you to understand, this is kind of like the easier problem first, and then we get to the harder one. All right, so what I really need to understand here is that the only issues, the only places we're interested in talking about are what's happening at 1 and 3. Y'all agree? Anywhere else, we know that these functions are well behaved. So I need to see if f is continuous at x equals 1 and x equals 3. Because that's where the interesting changes are happening. So these are two different things I need to look at, right? Let me look at the first one. And we're going to act like we don't have the graph. Is f continuous at x equals 1? All right. Well, to answer this, I'm going to write down what it would mean to be continuous at 1. For it to be continuous at 1, I would need this. The limit as x approaches 1 of the function to be equal to f of 1. Critical that you understand what I just did. This is just a definition of continuity at a point, right? A here is 1. So I replace the a with 1 there, I replace the a with 1 there. This means that as I approach, right, as I approach 1, from the left and the right, I should be equal to the function's value at 1. All right? Let's see if this is right. Let's see if it holds up. Does this hold? Can you tell me what f of 1 is?
Which side?
No, f of 1. Tell me what this is. So am I in the first part, the second part, or the third part? First part, right? Because this is x less than or equal to 1. So I'm going to use this one. Let's plug 1 into this, and what do you get? 3. Okay. So when you look at this limit, this equation, you want to work it like left and right side. So the right side we know is 3. The question is that equal to the limit of the function? So I'm going to write the limit as x approaches 1 of the function. Now I actually need to place a function in here. And this is big time. You have to understand this, all right? Which one do you put in there? That's what I'm getting at. Which function do I put in here? The top one, the middle one, or the bottom one, and why?
The middle one, because the first one's already defined at 1.
Yeah, this one is defined at 1, right?
You don't know if it's defined at 1 when it's x plus 2, right?
Let me do it this way. I think I know what you're saying, but I think I can do it this way a little easier. Let me go back to this little picture I had, okay? There's my picture, right? We know that at 1, we're on this parabola, right? Which is the top function. Is this going to be left continuous? Guaranteed, because it's defined at the point that comes off of its graph. We know we have left continuity here. We know it. The question is, do we have right continuity? Does this piece come in or not? Well, this is what I have to say. I have to say, as I approach 1 from the right side, right, which forces you into which function? Second one, because look, if you're to the right of 1, you're bigger than 1, aren't you? Just a little bit bigger than 1, and that forces you into this one. So that's why we're at x plus 2. And now take that limit, and what do you get? We get direct substitution in here, so what do you get? The left side is 3. And 3 equals 3. Check. It is continuous at 1. I was concerned that it may not be, but it actually is. These two functions come into each other. They go to the same place from the left and the right, and the dot